So this video is lesson 3 for Unit 5. We're going to take another look at definite integrals and just kind of looking at what we were doing last day. We talked about how Riemann set up this idea of sums, and he was pretty casual about the rectangles. They could be really of any width as long as you're picking some x values along the way for each ribbon to find the y's. That was fantastic. And then we took this story to the extreme. We said, well, what if we do a limit as the number of fence posts and fence runs goes to infinity? And we said, well, if you do that, that will actually be what we call the definite integral. That's this symbol up here at the top of the page. And that's going to represent the perfect answer, doing an infinite number of very, very thin ribbons. And we haven't really looked at a plan for how you could find these values yet, except maybe, you could rely on your feeling for geometry, for shapes, to find out what that area would be. And we're still not going to quite come up with a perfect plan yet for coming up with the exact answer. We're just going to refine the idea of, how you can write these on the page and what they actually mean and how you can maybe estimate them. So right off the start, if you want to find a definite integral using your calculator, if you're willing to do something that's just an approximation, well, then you can do that rectangular approximation method. There is actually a program that you can put on your calculator. I would actually advise that you don't use it. I don't think it's worth the time, but there is one that does work. And what you would do is you would put in the function into y1. So if I wanted to find the area under this one, x squared minus 4x plus a 6. Okay, that's great. And if I'm going from 0 to 5, I can actually ask this program to do that for me. So the program is called ramgraph. And I've got it right here. And if I fire it up, it says, okay, well, where do you want to start? Where do you want to finish? And if you are going to play with this program called ramgraph, then the starting value is what they call A. The finishing value is B. So I would say, hey, from 0 to 5. And then it asks you, well, how many ribbons do you want? And you can see for my estimates that are on the page here, I'm going to be going with 5 ribbons. It's not going to be a perfect answer, but it's what I'm going to go with. And then my calculator goes and draws this. And it says, okay, all right, I've got an answer for you. The picture might look like this. There you go. Here's what it looks like if it's left attached, if it's an LRAM. And the value for that is 20. Okay, great. So these are just estimates of these definite integrals. They're not the correct value. And then it could be like, oh, well, what about this? Attaching on the right. Here's the value for that. That ends up being 25. So again, not the correct value for the definite integral, but it's an estimate. And another way, what if you attach the ribbons in the middle? Still not the right answer, but maybe getting a little bit closer. And that one is 21.25. So none of those are right. Hopefully we can do a little bit better. And you can. Ultimately, there's a calculus way to do this perfectly. That's coming in the next lesson. But for now, we're just kind of getting comfortable with the story. If you've got the function in your calculator like this, I'm just going to go zoom 4 and take a look at that. It's not quite going to be wide enough here. Actually, I can't even see the function at all. Maybe I'll zoom out just a little bit more. Okay, and you know what? I'm not seeing anything here at all. And the reason for that is that program has gone and made some changes to my calculator. It's actually deactivated that. So that was a bit annoying. There's the graph. And I might want to go and ask my calculator, hey, have you got an estimate for how much area there is under the curve from 0 out to 5? And I can do that on the graph by going second, calculate, and then it's option number 7. And it's going to ask, where's your lower limit? Where do you want to start? Well, I want to start at 0, so I just type that in. I say 0, please, and hit enter. Then it says, where would you like to stop? Well, 5. And it's going to do a lot more than 5 ribbons. It's going to do thousands of them. And it says, okay, I've done thousands of them, and I've got this answer, 21 with 6s repeating. That's pretty darn close, right? I can kind of see the answer is 21 2/3. That's one option, is to use my calculator once it's graphed it to actually go and draw that picture. There are some options to do this if you don't want to do the graphing first, if you just want to kind of get going and get this to happen. And it would look like this. If you have a TI-83, it's going to look one way. And if you have a TI-84, it's going to look a little different. So I'll show you both. You would go in the math menu, I'll clear this all off. So I'm not in a graph. I go to the math menu, and it's down below It's not number 8, that's a derivative, but it's number 9, and then I hit enter. Now in the TI-83, it just looks like this. The first thing that I would type in is going to be the actual function. In this case, x squared minus 4x plus 6. And I could type all of that in right here, right? That would go in there, x squared minus 4x plus 6. Or if I've actually got it already typed into y1, I could just go and say y1, and it'll go and grab that. So I'm going to do that. So I've already got it on the go. So I go to vars, y variables, functions, number 1. Done. Then I put a comma in there. The next thing I put in is what's my variable that I'm using. Well, that would be x's, then another comma. Where do you want to start? A comma. Where do you want to finish? And then close my bracket. So lots of things to put in here, including this variable of integration, right? This dummy variable that goes in there. And then where do you want to start? 0. Where do you want to finish? 5. Now, if you have a TI-84, here's where everything goes. The 0 would go here. The 5 would go there. The x goes after the d. That says all the little ribbons have a width of dx. And in here is where you're going to put your y1, where you're going to put your function. If it's already in your graphing equations, you can say y1, or you could actually go and physically type in x squared minus 4x plus 6. Then you can hit enter, and it figures it out. Of course, it gives you the same answer, 21 with 6's repeating. Okay, well, I'm going to lean on my graphing calculator a little bit to see if I can get it to help me with some definite integrals for this example number 2. So it says use that feature to calculate the area underneath this graph, and it's displayed here in your notes. Y is equal to 2x. That's the graph I want to find the area under. From x equals 0, that'll be my start, to each of these stopping places. So we're going to try different places to stop and see how much area we get. Now the window you can see there is from -1 to 6. In fact, let me just get this going here. Clear that off. And I'm going to put in the function 2x. Then I'm going to go to window and say, okay, let's put in some numbers here. Let's go from -1 to 6. Tick marks every one. I'm just following what's in your notes. The y minimum, maybe -2, maximum of 20. Tick marks every one is great. So there's the graph. Fantastic, I can see it. Now I'm going to go and find the area underneath it and stopping at different spots. Really, the reason for this example, we sometimes do this as calculus teachers, it's a little foreshadowing for information you're going to see in the next lesson, right? Trying to figure out like, well, what is the general plan with calculus to do this story? Where we begin at 0 and then we're going to go and finish at some spot, right? Like some place B, right? Where we stop finding the area. So I'm going to do this calculation a few times. So here goes. Second, calculate. I'm going to do option number 7, right? So yeah, I want to find the area under the curve starting at 0. And the first row on the table says, let's stop at 0. Well, there's the answer. You don't have a chance to accumulate any area at all, right? So a big 0 there for the area under that curve from 0 to 0. Okay, let's try again. Let's go second, calculate. Number 7. How about we go from 0 to 1? Oh, okay, so you can see it's kind of filling that in, right? It's shading it in, and it says, well, if you go from 0 to 1, the amount of area is 1 unit of area. Okay, well, let's keep going. What if we were to go calculate number 7? What if we go from 0 to 2? We're going to get some more area in there. It's like, oh, okay, well, that's 4. Interesting. If I only stop at 1, I get 1. If I stop at 2, I get 4. Let's keep trying this. Okay, option number 7, starting at 0. So we're kind of practicing just this idea of using your calculator to help you out. If I go from 0 to 3, I get an area of 9. And sure enough, this pattern that's starting to develop holds true. If I go from 0 to 4, the area is 16. And last one, if I go from 0 to 5, yep, the area is 25. So it's kind of doing these, well, it's not kind of, it's doing these perfect squares of whatever stopping number I tried to stop at, which is kind of neat. Now, to try to get my calculator to graph that is actually pretty tough, but not impossible. I can say, hey calculator, would you mind trying to graph the results you get when you do this numerical integration of 2x, right? That's the function I want to play with. Let me clean that x up a little bit. So if you're doing this on a Chp5, you can say y2 is equal to, and you press that math button, and then you go down to like option number 9, and you say, hey, let's do this integral of 2x. And well, we're using x's, so if you have a Ti83, we're going to put an x in there, or if you have a Ti84, you're going to put the x here. And then you're going to say, hey, why don't we start at 0 for both of them? But then here's where you have to get creative. You have to say, when you're graphing this picture that shows you how much area you get as you work your way along the x-axis, can you keep going until you stop at whatever pixel we're currently at? So we're going to put an x in there. And this will find a machine that basically spits out the area so far function. Some calculators are smart enough to just know what this curve is, but the Ti83 or the Ti84 is not quite smart enough to do that. So I'm going to give this a try here. I'm going to go down and say, okay, math. Let's go down to option number 9. And we're going to go and do a graph of how much area do you get under 2x. X is the variable. Starting at 0, finishing at x. So pixel by pixel, it's going to keep track of how much area we actually get there. And here comes the graph. Okay, I can't see much at the beginning because it's hidden behind all that black stuff. So I think I'm going to have to get rid of that for you so you can see this better. I can also see how brutally long it takes to actually go and do this. It's a very, very, very slow process. And it's basically slowly, behind all that black, it's trying to draw this curve, which is just y equals x squared. So y equals x squared is actually predicting how much area there is under the graph of y equals 2x, starting at 0, and then finishing at wherever you want to stop. And it took a while for my calculator to get there, so I'm not even going to ask it to do it again without that black stuff. But it does seem that this area so far machine is just y equals x squared. Okay, that's interesting, because the derivative of x squared is actually 2x, right? And that's no accident, right? That's how this game works. Okay, just a few more pages here for today's lesson. We're going to look at some properties that you can rely on when you are looking at some definite integrals, these areas under the curves. And some of these you're going to look at and go, whoa, that is just so obvious, just geometrically, that it was going to be that. So here they are, some nice simple rules we can lean on. If you've got some function f of x, and we're doing a definite integral of f of x dx, that means let's go and get the perfect area under the curve. If somebody says, would you mind starting at A and finishing at A, just like that, well, you don't have enough time to gather up any area, so that answer is always going to be 0. Going backwards, what if you've got some sort of function, and maybe right here is A, and maybe all the way down over there to the right of that, maybe that's B. If the amount of area underneath, I'm going to make up a number just for the sake of what we're going to do here. Let's say the area in there is 5, right? If you could do the perfect integral somehow next day using some calculus. Okay, so let's say that's 5. If somebody was to ask you, well, what about this integral, right? So actually, let me put 2 on the page here. If somebody says, oh, I integrated from A to B, I found the area under that curve with this definite integral, and it was 5. Well, if you integrate from B to A, if you walk backwards, then the plan is every one of those little Riemann ribbons has a negative width to it. And so you end up with the same number, but with a minus sign in front. So those integrals will always be opposites when you have one of them integrating forwards and one of them integrating backwards. The next story, this one here is something called adjacent integrals. And I think once you see it, you'll look at it and go, yeah, okay, that makes perfect sense. What if you start this integrating, this finding the area under the curve process at A, and then we're going to stop briefly at B, take a little lunch break, but then we're going to keep on going over to C. and there would be a certain amount of area under the graph from A to B. And then there's more area, obviously, as we continue this definite integration process to find the area underneath the graph from B to C. And here's a little truthful statement about integrals that are right after each other. If you integrate from A to B, f of x dx, that means go and find the perfect area under the curve. If you ever catch yourself adding to that the integral from B to C, f of x dx, well, that's going to be the integral from A to C, f of x dx. They just add up, just side by side. All right, the next one here, constant function. This is one that maybe we don't need a lot of calculus for. If you've got a super boring function that just looks like this, y is equal to k, like y equals 3, something like that, well, I guess finding the integral is actually a pretty easy task because it would just be a nice rectangle that you're finding the area for. So if you ever have to integrate and you're working with a constant, right, if you ever have to do one of these definite integrals and it's for sure a nice constant function, right, just some k dx, well, that's a ribbon that's going to be k tall and b minus a wide. So the answer is just going to be k multiplied by b minus a. Okay, just some useful little rules that are going to help us out a fair bit. Got a few more on the next page. The next one, constant multiplier. I had trouble sketching this, as you can see. Right? Those look like pretty awful looking graphs. My hope was that maybe this lower one could be some function f of x, and then the upper one has been stretched. It's actually k times f of x, just multiplied by some sort of constant. And you might see somebody integrating these things from A all the way out to B. And obviously if that k is bigger than 1, there's going to be more area underneath that k times f of x graph than there would be under just f of x. So here's the rule for constant multiplier. It's the same rule that we had for doing derivatives, which was this. Constants. I gotta learn how to spell. Try that again here. Okay, this is gonna give me just a little bit of grief for a second. Give me 1 second. Okay, I think I've got this back working again. So here's the thing. Constants, they just hang around. No big deal. So if you're ever asked to integrate that tall function, k times f of x dx, so it's been expanded vertically by a factor of k, and you're integrating from a to b, if you would prefer, you could just integrate that smaller function, the original function, f of x dx, from a to b, but then what you're going to have to do is multiply your answer by k. So you can basically slide constants just outside of that integration sign. The next one, sums and differences. What if you've got a couple of functions? Maybe we'll call this one down here f of x, and the one up here g of x. And you're trying to maybe do some integrating from some starting spot A to some finishing spot B. And so you've got these two things. If you're ever asked to integrate the sum of those two things, well, f plus g would actually be like way up here somewhere. And the rule says this. If you're integrating from A to B, the sum of f of x plus g of x dx, you can do that actually just by integrating them separately and then adding. So you can integrate this one function, find the area under it, from a to b, and then add on the integral from a to b of g of x. Two last ones that are pretty rare, but if you catch them, they're nice. if you've got an odd function, something that maybe looks like this, does the opposite thing on the opposite side. On the rare case, doesn't happen often, but on the rare case where you're integrating from, let's call it minus a all the way out to a, because of the fact that calculus likes to call this integral here a negative number, because the area is hanging down underneath the x-axis, and it likes to call this integral positive because it sticks up above the x-axis. If you're ever integrating an odd function from negative a to a, only for odd functions, if you're integrating this story and you know for a fact that that f of x is odd, then the answer is 0. Those two areas are going to cancel out. Likewise, there's a bit of a time saver here if you know you've got a function that's even. It's doing opposite things on, or the identical things on opposite sides. If you're ever asked to integrate from negative a to a, well, those areas won't cancel, but they will look identical. So whatever area you have for this story, you've got the same area for that one there. So if you notice that you've got an even function, and if you're being asked to integrate from negative a to a, some f of x dx, if you desire, if you want to, you could just double this answer, integrating from 0 to a, f of x dx. Sometimes that can be a little bit faster. Not always, but sometimes. Okay, so those are some nice handy little rules. And we're going to look at just one more page here, and then this lesson's done. And then on the next lesson, we'll actually see how you can do in a nice calculus way correct perfect answers for these definite integrals. But now just some theory here. We're going to look at how calculus people calculate averages of functions. So let's say I've got a function up here and it's kind of wobbling around as time goes by. You can see it's a little bit above 3, then it's below 3, then it's above 3, then it's below. It's kind of just wobbling there. And if somebody tells you that the area in that shaded part is 24, and then they're asking you, well, how do I go and find the average for this function? Maybe starting here at 0 and finishing all the way up here at 8. Well, I know how to average numbers up. You just add them all up and divide by how many you've got. But how do I average a function, something that's continuously spitting out y values? And the answer is, you can see right here actually that the average height of this function seems to be right around 3. And so how does that relate to the 24 and the 8? Well, yeah, I can get to 3 by dividing, and that's exactly how we calculate averages with calculus. You'd want to say, okay, look, there's 24 units of area there divided by this span, this run that goes for 8, okay, along the bottom. That's the width of that story. And sure enough, you get this average height of 3. So that's what we're going to do in calculus if you have to find an average value of a function. So a formula for that, if you want it, how about this? Formula for average value. Average value of a function is going to be this. We're going to integrate the function. So we'll integrate f of x dx. That'll perfectly find the area under the graph from a to b. And then we're going to go and divide that by how wide that run is. We're going to divide that by b minus a. That will go and figure out the average perfectly for us. So we'll try this out here with example 3, where it says, can you find the average value of 3x squared on the interval from 2 to 4? Sure. One of the things I'll have to do is I'll have to integrate from 2 to 4. I'll have to integrate this function, but that's doable. Right? So we'll do that first maybe. From 2 to 4, trying to integrate 3x squared dx. Okay, well, right now I don't have any plan for doing this. That comes in the very next lesson. So maybe I'll just have to go to my calculator and say, okay, calculator, can you find the area here So I'll go in and type this in as a function, 3x squared. Maybe I'll try zoom 4 off the start, see how that looks. Well, I can't really see all the way up there to the top. Maybe I'll change my window just for fun. So my y max goes up a lot more. I don't know, let's go up to about 60. Tick marks every 10. Okay, yep, that's not bad. Now I'm just going to ask my calculator because right now I don't know how to do this. So until I learn this calculus process next lesson, maybe I'll just go calculate option number 7 from 2 all the way out to 4. And it sits there and thinks about it and says, okay, I got it. The area there is 56. And it did that with a whole bunch of little Riemann ribbons. Okay, so that's how much area there is under the graph. If somebody's asking me, well, what's the average value for that graph? On average, how tall is it? I would take 56 and divide by the width that happens from 2 all the way to 4. Well, that's a width of 2. And so the average value of that graph is 28. That brings us right into the second half, the second flavor of the mean value theorem. Okay, so we've already done the mean value theorem for derivatives. Now we're going to do the mean value theorem for integrals, right? Let's actually compare and contrast them side by side. So the one we've already seen for derivatives says this. If you've got a function that's nice and beautiful, it can't be kind of weird looking, right? It's got to be continuous. It's got to be differentiable on the inside. So if we start, here, maybe at A, and we finish all the way down the road here at B, then this rule for derivatives says that if a kid in grade 10 goes and finds the average slope between those 2 points, right? If they play around with a secant line, then somewhere along the way, at least once, there's going to be a grade 12 tangent line that actually shares the same slope as that grade 10 secant line. So the rules for the story, it had to be a nice function. It had to be continuous. All of our theorems require that continuous on that closed interval from A to B. And if it's smooth, if it's differentiable, at least on the inside, then somewhere along the way, we don't know exactly where, but somewhere along the way, we'll call that place C, this is going to happen. The kid in grade 10 who says, hey, if I do a slope calculation on that green line, I get the same answer as somebody in grade 12. So the grade 12 student is saying, yep, f prime figured out at this point. It's going to happen at least once. That's equal to the exact same slope as the kid in grade 10 who says, oh yeah, I just did a little grade 10 averaging slope. I did f at b minus f at a all over b minus a. It's going to happen at least once. Now, here's an example of a story that doesn't work with the mean value theorem because it's just not continuous or not differentiable, right? Like the story has to only work with, well, it will only work for sure with things that are continuous and differentiable. So if you've got a picture that looks like this, then yes, it's possible that some kid in grade 10 could come along and draw in some sort of secant line in here and say, hey, your graph never ever had that for a tangent. It doesn't violate the mean value theorem. It's just that the mean value theorem doesn't apply. Okay, well, that's old news. That's old news. Here's the other half of the story for integrals. Okay, so this is the average value theorem, the average value rule, and this is the one for integrals. Let's draw ourselves a nice continuous function, just like this. Maybe we'll go like that. So if f of x is continuous, notice that this half of the mean value theorem doesn't care if it's differentiable or not. It just needs to be continuous. And we're going to go and check out kind of an averaging story here from A all the way up here to B. Here's what this story says. At some point along the way, I'm not totally sure where, but at some point along the way, this function, f of x, this function at some special little value along the way has to equal the average value of the function. Has to actually equal this. Here's me calculating the average value of that function. 1 over b minus a, right? There's me dividing by the width, and then integrating to find the area. Starting at a, finishing at b. So in other words, right, this i.e., in other words, at some point f of x will equal its average. So if you were to go and very carefully find the area underneath this graph, take that yellow area, divide by the distance from a to b, right? That's what this 1 over b minus a is doing. If you find that average value, right, and let's just say that this average value puts you, I don't know, maybe somewhere in here for the average value, then at some spot along the way, this graph is going to hit its average at least once at some c value. Doesn't tell you how to find that c, it just says, oh yeah, it's going to happen at least once. The graph has to be continuous though for that to be true. So here is a poor example because, well, this mean value theorem just doesn't need to apply. What if your graph is steady at some low value and then it just decides, whoop, I'm going to jump up now to this value. It just does a little step up into the air. And I might start my story here and finish my story there. And the mean value theorem just doesn't apply in this story. You know, I could still try doing that deal where you integrate to find the area underneath. Got some area here, and then it clicks up like this. I could go and find that area, use it to help me find the average value of this function, and I might find, oh yeah, the average value of the function's right here. But that blue function never ever touches that average value. It didn't have to. There was no requirement that it would do that because this wasn't a good function. It just wasn't a continuous function. That actually not only completes the lesson, but it completes all of the theorems that we need to know for AP Calculus. We've seen all like 3.5 of them now. The intermediate value theorem, the extreme value theorem, and both mean value theorems. And those are all the ones that we need for the course. And that wraps up our lesson as well. And in the next lesson, we finally get to see how do you go and perfectly find these areas under the curves.